So welcome to the third week of catalyst stability. Today we're gonna introduce you to the field of the catalyst deactivation. So mainly it will uh, discuss about how the catalyst deactivates during the reaction and how to recover it. But first, let's review the last lecture about the introduction of the catalysis, and then we will go through the homeworks that you guys sent. After that, we will go into the topic, the today's topic about the catalyst deactivation. So let's review on the components of heterogeneous catalyst. As we learned last lecture, that for the heterogeneous catalyst, they have three main components. The first part is the active site, then we have the support and the promoter. The active site can be metal, metal oxide, metal sulfide, and so on. So is the region or the location where the reaction proceeds and you form the products, together with the byproducts in some reactions. And this is the uh, although although it is not the only place that the reaction proceed, but the majority of the reaction proceed at this area. Next is the support. This component acts as a region for you to disperse the active sites. And if you have high surface area support, uh, the support with high surface area can distribute or disperse your active site in high quantity per gram or the per weight of the catalyst that you used. Also, as we mentioned last time, that the MSI or the metal support interactions is a really important factor to determine the activity of your catalytic materials. So if it's too strong or too weak, the reaction will not proceed well. And as we have three types, you can uh, have a look at the last lecture, as we have the weak metal support interactions, the medium, and the strong. The last component you can have or you may not have in your catalyst. That's fine, but if it exists in your catalyst, this component will promote uh, the properties of your catalyst, as we classify it into two groups. The first one is a textural promoter, and the second one is a structural promoter. The textural will enhance the physical properties after you add it to the catalyst, but the structural promoter will enhance both the chemical and catalytic properties, in which after this after we have mentioned all the components of the heterogeneous catalyst in the last lecture, we then go through each properties of the catalyst, right? So then I would like to review you again about these properties. So these are the properties that you will find and you can measure in your catalyst. For the physical properties, some important properties in this classification is the specific surface area and the active surface area. If you have high the materials, the catalytic materials with high specific surface area, it can enhance the activity of your catalyst because you can disperse a lot of active sites onto the support. So after we have mentioned the surface area, uh, some definition um, to make the surface area more meaningful, they will represent the only the important part of your catalyst. Uh, as we can see in the next properties, the active surface area is the surface area only the region that you have the active site. So this one will represent the catalyst more effectively. For the crush strength and the attrition resistance, this one can be seen as the mechanical properties also, and also an important factor when you operate at larger scale, when you need the catalyst to be packed in your reactor, and during the process, the strength and resistance to attrition is important for your catalyst to withstand the incoming flow if it's high enough that can crush your catalyst, and or even make your catalyst move and crush together, in which the attrition will make your catalyst become powder, and it will block the process and the equipment next to the reactor. The next one is the chemical properties. As we see, there's four important properties in chemical properties. Some important property is the oxidation state, in which if you have the same element but different state of oxidations, you will have different catalytic activities. Also, together with the electronic structure and acidity and basicity. As I would like to uh, I would like to inform you again that every time we talk about chemical properties or about chemistry, it all involves electron. So these four properties involve if for the catalyst with different chemical properties, it means that the behavior of the electrons is different. Also, the acidity and basicity can be represented as the movement of the electron. The difficulty in terms of the difficulty of do, of the donation of electrons, like in the definition of acid and base by Lewis, as you can review on the last lecture. The last property is the catalytic one. As we know that the intrinsic activity counts only the activity per the active site that you have in your catalyst, and the activity represent how well can your catalyst convert the reactants, but not considering how well your reactant goes to the main product. So if your catalyst is very active, but it all convert the reactants to the byproducts, it will not be a good catalyst. So that's why they consider the second factor, which is the selectivity. This one we consider the rate of the production of your main products to the byproducts. So now you have the catalyst that now you evaluate your catalyst if it's active and selective. But if your catalyst can run the reaction, can catalyze the reaction at a very short time, they will cause the burden to your process. You have to pay for the change of the catalyst or the regenerations. So the last factor is really important, and it comes as the main theme for this course, is the stability. The stability can be measured in many terms, depending on your reaction, on and the cause of the activations, in which we will talk about this all throughout the course. So let's review the homework that I asked you to do. This one is an example that I gave you, and let's see how it goes. First one is the physical properties. So as I said that I would like you to find a paper and read it and then digest and answer my questions. So I would like to classify the homework into three types. So now the one that find the physical properties that I asked, here's an example. So this person referred to the paper in the International Journal of Hydrogen Energy, which was published in 2017, and that the person found that the paper they use the nickel as the active side, while they have the support of aluminum or the alumina or the aluminum oxide. Also, they use the promoter as cerium to enhance the catalytic activity. Then he gave an example of the sentence that the surface area of the 25 nickel supported on the ceria alumina is 234.4 square meter per gram. So he gave an example of the physical properties, which is the surface area. So this is a good answer and a probable one. Next, I pick the example of the students in the class that I give an example about the chemical properties. So this person referred to the paper in Applied Catalysis B Environmental, which was published in 2017. So he found that they use the catalyst, which has the active site of zirconium, and which was supported on the beta zeolite. And they use the promoter as the HPA or the heteropolyacid, in which HPA consists of the phosphotungstic acid and the silicotungstic acid, or HPW and HSIW. And he gave a sentence stating that the total acidity of proton silica tungsten supported on zirconium beta zeolite is equal to 0.71 millimole per gram. So he gave an example of the total acidity, which is the chemical properties, and this homework was done right also. The last example that I would like to give you that is as a person give filed a paper and give an example about the catalytic properties. So this person referred to the paper from Journal of Catalysis, which was published in 2009, in which this paper they use the active site as rhodium supported on titanium, and they introduced iron as the promoter. And he gave an example of the TOF or the turnover frequency as the catalytic properties. So as of now, we have reviewed all the components of the last lecture. I would like to start today's lecture into the introduction to catalyst deactivation. So we're gonna talk first about the main idea of catalyst deactivation. As you can see on your right is the industrial catalyst, which is extruded and synthesized to be in a form that can be packed in the reactor, the industrial size reactor. And here on your bottom left is the fresh catalyst, and on the right is the spent one. When it go through the reactions and become deactivated, you can see the changes in color, but color have no meaning if the activity still remains high. The main point is that the activity drops when it deactivates. So we will see the mechanisms on the deactivations. So the reference that we'll use is based on the review paper that was written by Professor Arca and Professor Bartolomeo from the Brigham Young University. So Professor Bartolomeo is the expert in catalyst deactivation. And if you have any question, you can refer to the reference. So we will continue first. So the catalyst deactivation can be classified into 6 schemes. The first one is the poisoning, in which we will talk in depth today, and the rest will be in the later week. Second type is the fouling or the caulking, which is caused by the carbon-based substance that will deposit on the catalyst and will reduce the activity of the catalyst. The third one is the thermal degradation, or we can call it sintering. So this one causes the loss in the active site by the fusing. So the small active site fuse together, reducing the surface area of the active site. So when the surface area is reduced, your activity will drop. The fourth one is the vapor compound formation or the leaching. So this one is a loss of the active site by leaching of the active site from the support. The fifth one is the vapor solid reaction and solid solid reaction. So these reactions cause the loss in activity of the active site. And the last one, this one is based on the deactivation by the mechanical mechanisms. So the attrition and crushing of the particles, the catalyst particle will make it lost not only the active site, but the if it was crushed into powders, it will lose during the process. So based on 6 types of catalyst deactivation, we can group it by the nature of the deactivation mechanisms. First one is the mechanical, followed by the chemical, and the last one is the thermal. So as you can see here, that the mechanical deactivations consist of the fouling, or in which we can call caulking also, and the attrition crushing, because the fouling can cause the breaking of the catalyst particles also. But we can see it more clearer on during attrition and crushing, that is it caused the mechanical failure to the particles. Next, for the chemicals, you can see that the poisoning, is almost always, no, it is always the chemical deactivation, because it has the chemical bonding and the effects from the chemistry on the active site. Fouling and caulking, as it also can be solved on the active sites, it also deactivates the catalyst chemically. Next is the thermal degradation or sintering. This one, as I told you, that the active site fuses together. The fusing of 2 active sites cause the bonding between them. So every time the atom bonds to other atoms is the chemical reaction, right? So this one is considered as the chemical deactivation. The last two is the vapor compound formation or leaching, and the vapor solid reaction and solid solid reaction, as the name says, is the chemical reactions. Leaching is also since we lost the active site from the support because of the breaking of the chemical bonding between the support and the active site. So in here, if you refer to the last lecture, the metal support interaction, or the MSIs, is an important factor to control the leaching. So it can control the deactivation. The last group is the thermal. The thermal deactivation is they consist of thermal degradation and sintering, since the high temperature can cause the fusing of the active sites. As I highlight here, the yellow highlight on coking, you can see that it intercepts between the mechanical and chemical, while the thermal degradation sintering intersects overlaps between chemical and thermal. So these two deactivation schemes occurs as both mechanical and chemical for the fouling, and both thermal and chemical for the thermal degradation and sintering. So let's talk about the first type of deactivations. Poisoning, as it is classified as the chemical deactivation. What is it? Occurs as the strong chemisorption of species on the catalytic sites. So the catalytic site is the active site. So this chemisorption, this strong chemisorption of species, cause the blockage. So it blocks the active site. So what happens if you block the active site? As the active site is the main region for the reaction to proceed. So when your reactant comes in, it needs to react at the active site to further form products. So if you have less of the active site, you can convert less reactant to products, causing the dropping of the activity, and your yield of products will decrease. So this during the poisoning, you lost the active site, which resulted in the loss of activity. So talking about fouling and coking, which is both the mechanical and chemical catalyst deactivation. It's the physical deposition of species from fluid phase. So fluid includes both either gas or liquid phase, depending on your reactions. So is the deposition of the species from either liquid or gas phase onto the catalytic surface, so onto the active side of the catalyst and in the catalyst pore. Why is it so important to control this type of deactivations? It's because firstly, although the species came as the chemical deactivation by the deposition on the active site, covering the active sites and blocking the progress of the main reactions. As it comes as the chemical reactions, it just lower the number of your active site. But importantly, the coke, in which the coking species, which comes in from the reactants, it can propagate to form a larger size of coke. And these cokes, in higher quantity, it can cause the pressure to the catalyst pore. So this pressure will make the catalyst break and collapse. So the breaking of the catalyst particles will result in a formation of the powder. So as the large catalyst particle becomes powder, it will block the reactor when during the operations. So as it came as the chemical deactivation, propagating to the mechanical deactivation, it completely deactivates the process. The third one is the thermal degradation and sintering. It's also it is also classified as both thermal and chemical catalyst deactivation. So uh, when this type of deactivation occurs, it's caused the loss of active sites and the active area. The process, the mechanisms of this type of deactivation is thermally induced. So it means that it is induced by the temperature applied from the process from the into. So as you set the temperature to your reactor, the high temperature that you set will induce the loss of the active sites by the fusing of the active sites. So, for example, if you have 10 particles of catalyst in the size of 1 nanometers, and when it fused to form a one large bulk catalyst particles, it lost the surface area. So it means that you lost the large amount of active sites. So this thermally induced process caused the loss in activation by the loss of surface active surface area, and also the loss of the active phase to support reactions. So for example, you have a catalyst supported on the support. When you lost the active site, um, you lost the interaction between the support and the active phase. Going next onto the fourth type of catalyst deactivation, the vapor formation, which is the chemical deactivation. So this vapor is the vapor of the active site. So your active site will evaporate. So it means your active site was lost as a vapor into the solution, or for example in gas phase it will lost into the gas. So this occurs from the reaction of gas, the incoming reactants, or even the byproducts, the products with the catalyst phase, to produce what? To produce the volatile compound. So this volatile compound is specific. Not, not all reactions have this kind of deactivation, but only the right combination between your reactant products or byproducts with your catalyst uh, can will cause this kind of deactivation. So we will talk about all this later. So for the fifth deactivation schemes is the chemical deactivation, is called the vapor solid and solid solid reactions. So if the reaction is a chemical reaction of vapor, support, or promoter with catalytic phase. So why vapor? In this case, as it is the vapor solid reactions, the vapor is the reactant products or byproducts in the gas phase. Since we have the gas phase reaction, so this vapor will react with the catalytic phase. So what is the catalytic phase? From last lecture, from last lecture, we learned that the catalytic phase is the active site, in which it can be metal oxides, metal carbide, metal sulfide, so on. This catalytic phase, when reacting with the vapor to form the inactive phase, uh, it will cause the deactivation in the catalyst. But that will be typical because, as you know, that some byproducts will cause the deactivation either by poisoning, covering the active site. But for the severe one, it will react with the active site to form the inactive phase. So although you have the same surface area, your active site now changes to the inactive form. Also with the support, although we support the callus onto the support, and the support should be supporting the catalytic properties of the catalytic phase, but sometimes at high temperature, the reaction between the support and the catalytic phase can occur. So this one, it becomes solid-solid reactions. So it's the solid state reaction, if you would like to further search for it. Also with the promoter, not all the promoter that we added will enhance the catalytic activity. So it will, it enhances the catalytic activities, but at some specific temperature high enough, it will react with the active site to form the inactive phase. So to summarize, this kind of deactivations is the reaction between either reactants, products, byproducts with the catalytic phase. This one is vapor solid reactions, and if the solid-solid reactions, or we can call it solid-state reactions, occurs, it will come from the support or promoter reacting with the active site. So all of which will form the inactive phase. So the last form of the catalyst deactivations is the mechanical one. So this one is attrition. It can either be alone or combined with the crushing. So these two main schemes will cause the loss of catalytic materials. So not only the active site, but the support, it will be lost together due to what? So this is caused by the abrasions. So when two particles comes into contact, and one particle exerts a force onto the other, causing even the frictions, everything that create force it can cut or make or crush the another particle nearby. And at high temperature and high flow of feed, either gas or liquid, it will cause the abrasion and you will lose the materials. And as you pack the catalytic materials, you will lose the catalytic materials and you lost the activity. Then it means that you lost the productivity, you reduce the production of the products, and your profit will be reduced also. So this also causes the loss of internal surface area due to the crushing of the particles. So as we saw that the catalytic materials are lost from the system together, the crushing can cause the loss of inside surface area. So if the whole particle is crushed, the internal surface area in which we deposit the active site in is lost also. So although it's a mechanical deactivation, it directly links to the activity of the catalyst and also the productions of the products. Since what? Since uh, the loss of the number of active site, it will reflect totally to the total conversions, since the conversion of the reactant to products is the activity of one active site times the number of the active sites you have in the system. So if you lost the number of active sites, you lost the total conversion, and you can convert less of the reactant to the products. So here's the reference used today in which you can have a look. And if you use the VPN from the university, you can even download it. And if you have further questions, you can post it in a discussions tab as before. So the homework for this week, I would like you to find two papers that has different types of catalyst deactivation. So the first and the second paper that you have found uh, should must have different deactivation schemes, and then you answer these questions. So like before, answer it in the answer sheet in the next two slides. I would like you to do the same to capture the title of the paper. Then you paste the link, online link, in which I can check the source. Then you answer what catalyst they use in the work, and then what reaction. You write it as the chemical reaction and the process, and then you answer what's the activation schemes, and describe what causes, or if it's more than one, what are they that cause the deactivation in the process. And then the same, you export to picture and upload to Coursewheel before the next class. And thank you for coming to the class.